He's a director at MPI in Tübingen, and he also is affiliated with Amazon, and it's really a great honor to have him here. Let's welcome Bernhard.
Okay, thank you very much for this kind introduction. Thank you for coming here. This is an impressive audience. I remember I gave a NIPS invited talk about 10 years ago, and the audience of the whole NIPS, the audience was probably almost half of this. So it's impressive how this has all developed. So I was invited to this workshop. At first, I was a little bit puzzled because I had never worked on interpretability, even though I find this a very interesting topic. But then I started thinking about how this could be connected to causality, and I exchanged an email with the organizer, and I told them what I could talk about, and then they told me this is relevant. So hopefully you'll find it relevant as well. And maybe after the talk you'll agree that causality has a role to play. And I want to first have a general introduction and talk about this role, and hopefully sensitize you for the problems, and then I'll use that as an excuse to also talk about some recent development in learning causal mechanisms. Okay, so I'll start with the general part, with the simplest possible sort of experiment or data set, which is this one. So this is a data set that has a number of storks living in Germany and the human birth rate. And as you can see, there's a strong correlation in this data set. So given the number of storks, we can predict the human birth rate with pretty high accuracy using a linear model. And if you look at the numbers, I don't know if you can read them from the back, then it works out such that for every pair of brooding storks, we have about 500 new babies per year. So if Angela Merkel were to call Donald Trump, she could tell him that number, and Trump could use it for prediction in the US, assuming the relationships are the same. However, this begs the question, how should Angela communicate this model to Donald in a way that he would be able to interpret, let alone understand? And it turns out that actually, even though this is the simplest model imaginable, it just has one parameter, it's a non-trivial problem. So we can't simply say that each pair of storks brings 500 babies per year. I think none of us would believe that. So the model cannot be interpreted in that way, and it turns out if you think in detail what the model actually says, then it's only valid in a certain IID setting. So you could construct a setting such that this model correctly describes a certain random experiment, and Angela Merkel is a physicist, so maybe she could explain this random experiment to Donald Trump, but we don't know if Trump would understand it. So, and also chances are that he's not interested in prediction. He might be more interested in intervention. And intervention has something to do with causality. So suppose Trump wants more babies to be born. Should he change the number of storks brooding in America? So it's complicated. So overall, we can conclude at this point, even though this model is as simple as it gets, it's probably still not really interpretable or understandable without further explanation. So this leads us to the relationship between dependence and causality. And the first person, probably the first person to understand this relationship was Hans Reichenbach, a very interesting physicist and philosopher who worked in Germany at the time and then had to emigrate during the Nazi period. And he postulated what he called the common cause principle, which says that if we find two observables, x and y, that are statistically dependent, then there exists another variable z that causally influences both of them. And this variable z can be chosen such that it explains all the dependence between x and y in the sense of making them conditionally independent, so independent when conditioned on z. And as a special case, this variable, so that's the generic case, as a special case, the variable could coincide with either x or y. So if we consider the babies and the storks, if the storks bring the babies, this is the correct graph. If the babies attract storage, this is the correct graph. If there is some other variable that causes both, which could be economic development or it could be a time variable, then the red graph is correct. Now, the crucial insight is without additional assumptions, we cannot distinguish these three cases based on observational data. The class of observational distributions over x and y that can be realized by any of these three models is the same in all three cases. So this means we get the same statistical model, but we have different causal models if we interpret these arrows as causation. So a causal model contains generally more information than a statistical one. Okay, so let's think a bit more about causal models. So there's a beautiful theory of graphical causal models developed by Judea Pearl and others. The central notion, or a central notion, is the notion of a functional causal model or of a structural equation model. And in this model we have a set of observables living on a directly cyclic graph. The arrows between these observables represent direct causal links. And each variable is a function of its parents, PA are the parents of the graph, and a noise variable. So this is the only place where noise comes in, the functions are deterministic. So there's a little bit of noise injected at each node, and the noise variables are jointly independent. So this model entails a distribution, so there are no loops in this simple case, cyclic. So given the distribution of the noise variables, we can compute the induced distribution over the variables xi, and it turns out this is an interest distribution which satisfies the so-called causal Markov condition, which you probably all know from graphical models. So it's a certain conditional independence property, and in fact every graphical model can be realized like this. So every graphical model we can think of as the distribution induced by a structural equation model with certain independent noises. So the interesting thing is there is this conditional independence property, which means that we feed in independent noises, and then the distribution of these noises transformed into a distribution over the xi. It sort of picks up a footprint of the graph topology as the noises spread through the graph, and this footprint can be assayed using conditional independence testing, where of course every conditional test involves at least three quantities, A independent of B given C. So we can only do this if we have at least three variables xi. Now, we thought a lot about the problem, what happens if we have only two variables, and it turns out this forces you to think whether there are other types of assumptions that you could use for causal inference. And we looked at one of those assumptions in detail over these last 5 or 10 years. And I want to talk, the rest of the talk, I want to talk about this assumption and how this is connected to our interests. And to introduce this, let's look at a simple cause-effect problem where we only have two variables. So here I have a data set of temperatures. So these are average annual temperatures of different weather measuring stations in Germany. So you can see most of them are somewhere between 0 and 1,000 meters altitude, but some of them are higher. And overall, as it gets higher, the average temperature tends to get colder, which is consistent with what we expect from physics. And so we would probably believe that the correct causal structure is that the altitude controls it, or is the cause of the temperature. Maybe not precisely, but approximately this should be the correct causal structure. If we change the altitude, the temperature would change. So this would be the correct decomposition of the joint distribution according to this causal graph. Now, well, we could think about how do we get to this? What are the ways of establishing this kind of causality? Then, of course, the gold standard would be to do an actual intervention experiment. So that would be we build a big device to raise the weather station or maybe the city where it's built. Then we lift it up, we measure the temperature, we find that the temperature changes. Therefore, altitude causes temperature. That's good, but we wouldn't want to do it in practice, and probably we don't need to do it in practice. I can probably convince you to believe in this causal structure without doing that experiment. You probably already believed me in the last slide, and if you think about it, why do you believe me? Well, you probably do a hypothetical intervention. You imagine you lift the altitude of that place, and you would still think that this causes a change in the temperature because you know of some physical mechanisms imply certain temperature changes, or that imply that the temperature is a function of the altitude. You know that the pressure of the air changes, maybe the wind is different, there might be all sorts of mechanisms. You believe there is this physical mechanism P of t given A, which applies no matter what we feed into it. So it doesn't matter what kind of altitudes we go in. There is this mechanism, maybe it's a noisy one, maybe it depends on all sorts of other variables that we don't talk about here, but you believe there is a physical mechanism that's independent of this object here. And you would probably also believe that this mechanism is to some extent invariant, for instance, across different countries in a similar climate zone. So if you take Switzerland and Austria, they're both in the Alps, then maybe it's the case that the Swiss put their cities or their measuring stations into different places. Maybe they tend to be higher than in Austria, I don't know, but you would still maybe think that the overall mechanisms is the same. So if you would think a place that's higher in Switzerland probably will end up colder, just like a place that's higher in Austria. So we would think that this object is not just independent of the other thing, but it's also maybe to some extent invariant. So this is an invariant property of the world. So I'll give you another example of what we have in mind. This object is called a Bechet chair, and when you see this object, then your brain makes the assumption that the thing and the mechanism by which the light from this object reaches your brain are independent. We can violate this assumption. In this case, we violate it by looking through this hole, so that's a very specific vantage point. And if we do that, perception fails, because you see something which in reality isn't there, so perception misleads you. Now, I argue that in the generic case it makes sense to believe that the independence between object and the perception process holds true, or it makes sense to make this assumption because usually it holds. So I know our brain uses this all the time, so we assume that the object is independent of the vantage point. We also assume that the illumination is independent of the illumination. We assume that maybe the shadows don't line up with texture boundaries, etc. Or it doesn't happen that sort of 3D structures magically line up in 2D, even though they're different in 3D. So we make these kind of assumptions. It's overall called the generic viewpoint assumption. And if you move around an object, we also assume this because we can do something which is called structure from motion, which basically says you move around an object, what you see changes, but you assume the object itself doesn't change, and therefore you can combine your knowledge from the different directions to infer the 3D information. So let's assume overall that we have a causal generative process which is composed of autonomous modules that do not inform or influence each other. So I'll get a little bit more formal again and look at the factorization of this causal graph or graphical model. And so we always get we can always write down such a factorization of joint distribution according to these causal conditionals, which are the ones where we condition each variable on its causes according to the graph. So let's assume that this factorization is such that these objects here are independent, not in the sense of random variables, but independent in the sense that none of these objects contain information about any of the other ones. And if we change one of them, it doesn't imply that any of the other ones magically has to change at the same time. So generically, we would assume these are different components of the world, different mechanisms that we can independently change. Now, if I would argue, whenever something changes in the real world, it's in the end ultimately down to a change of one causal conditional. If we talk about this level of detail in our models, so there's at least one of those things that changes. Maybe sometimes we change multiple things at the same time, but suppose one of them changes. So that one condition changes means either one of the functions changes or the noise variable changes or both. Then we would expect that the others don't change, and that's nice because it means that two models still have something in common. However, if we were to write down this factorization according to a different graph, so often we can write it not just with respect to the causal graph, but also with respect to other graphs. And then it would generically be the case that if we change one mechanism, of course, changing one mechanism would always change the joint distribution, And in the generic case, if we then sort of write down the wrong factorization of that generic overall distribution, if this has changed, then every single term over here will change. So if we take the wrong decomposition, everything will change at the same time sort of to compensate each other's changes. That's an intuition for something that I will want to get at in the next slides. And I believe such a factorization changes simultaneously will lead to changes that are hard to interpret because they are not associated with mechanisms that change. Now here's maybe a simpler example. This is based on something Joshua brought up, Joshua Benjo, in a workshop just before NIPS, so a week ago, or a little less than a week ago, which he called the abstraction challenge for unsupervised learning. And the problem posed by Joshua is, why is it so much worse if we directly try to give a probabilistic model for sound or for acoustics? Why is it much better to decompose it as a product of probability distribution over phonemes times a conditional of acoustics given phonemes? And a causal explanation to make this plausible would be to say that this second formula is a decomposition into causal conditionals. So no matter what phonemes I want to produce when I give this talk to you, I will always use approximately the same red conditional. So if I were to give a talk about literature, I would still use this red conditional, even though the overall thing maybe would look different. This means that the conditional is an invariant, this red thing. I think it also means that it probably tends to be better interpretable than this very high-dimensional direct model at the top. Here's another interesting example. This is also shown from a talk at this workshop a little less than a week ago from a talk of Pietro Perona. It's a nice example of from computer vision. So we all know there are these fantastic image-based classifiers now. You give them 3 different images of cows, and in all cases the top hit here of the classifier is a cow. So that's very reassuring, and it gives us we get human performance. We have the feeling our machines can recognize cows as well as humans. But then we get these strange failures, and Pietro found these failures here, where you look for cows on the beach, and then it turns out that it doesn't work anymore. So in one of the cases, it's the number 6 hit, and in several cases, the cow doesn't show up at all. And I think these failures, they can occur whenever we learn non-causal conditionals. So, and I think it's an interesting problem to think about how this is actually the direction of the causality is related to this notion of adversarial examples. Okay, there's an implication, and I'll do this very briefly, of the independence principle for thermodynamics. So this is something for the physicists in the audience. To see this, suppose we have a beam of particles, which we think of as the cause, scattered at an object, that's a mechanism, then the outgoing beam, so these arrows going out, as the effect, they contain information about the object, and that's what makes vision possible. Photons contain information about the object where they have been scattered. Now we know that microscopically the time evolution is reversible, so that's always the case. The Schrödinger equation is reversible. Nevertheless, the photons contain information about the object only after the scattering and not before. So why is that the case? Why is it the case that photographs show the past rather than the future? And the reason, one can argue, is the independence principle. And we have formalized it in terms of algorithmic independence, so according to the model of complexity. So for this formalization, we suppose that S is the initial state of the system, M is the dynamics, let's say for simplicity applied for some fixed time. And then we postulate, that's the independence principle formalized, we postulate that S and M are algorithmically independent. So knowing S does not enable a shorter description of M and vice versa. If we assume this, then we can formally prove that the model of complexity is non-decreasing in this setting. So this means if we apply M to the state, the mechanism, then afterwards the model of complexity will be at least as large as before. And this can be interpreted as saying that the entropy of the state monotonically increases. And that's known as the second law of thermodynamics. which gives us the thermodynamic error of time. So the asymmetry here, which microscopically isn't there, comes from the assumption of the independence of the input conditions, so the initial state, and the dynamics. And it's, of course, this interpretation relies on the fact that some physicists consider the model of complexity actually an interesting measure of physical entropy. Okay, so here's a little bit closer to machine learning, where we can use the same principle to do cause-effect inference, which I mentioned before is a problem that cannot be solved using the Markov property because we need at least 3 variables to do conditional independence testing. And so in this case, we have a cause variable, the input distribution. We have a mechanism, which is actually even deterministic in this case, so no noise. That's our conditional. And then this distribution, this function together with the input distribution produces some output distribution. And what you can see is if you just start with a generic input distribution that knows nothing about the mechanism, so independence holds true, then the output distribution or the output density will have large mass wherever this mechanism was flat. So somehow the mechanism has left a footprint which is observable in the output density, and this can be formalized. And we can also here we can formalize a certain type of independence between mechanism and input here. So it's a certain property that involves the input density and the property of the mechanism. And if this independence holds true in the forward direction, then we can prove that it's strictly violated in the backward direction. And one can actually practically use something which is derived from this principle to solve cause-effect problems, so to decide, given the data set, what is cause, what is effect, and we can do it roughly in 3/4 of the cases. Okay, so and we've used this in different areas of machine learning. So one nice application is an interesting relationship to semi-supervised learning, or one can make certain predictions about when semi-supervised learning makes sense or works. Also, this idea that causal conditionals are robust and will transfer better to other tasks has been studied in various domains, and I should say that also is related work on what they call transportability. Okay, so now I come to the final part, which is an actual concrete algorithm inspired by this. So this is going to be connected to neural network learning and learning of mechanisms. And in this application, we assume we have data drawn from some canonical distribution. We use MNIST for simplicity. This data is then transformed by by a number of different mechanisms. For instance, one mechanism could be to add noise, another one could be to invert the image, and then we have mechanisms shifting in different directions. And now we want to come up with a learning algorithm that will, given this kind of data, but without knowledge of what were these mechanisms, how many there were, which one was applied to which digit, without this kind of knowledge, recover both the original digits and the mechanisms. And the method will be something similar to a gun, so it's a kind of generative model with a competitive training procedure for the mechanisms. So what we do is we feed in a digit, we have our mechanisms that are initialized to approximately perform the identity. Each of them gets a go in parallel at this exam, so they produce certain outputs. Then we score the outputs using the discriminator of a gun, which is trained on the original MNIST set together with this. And then the one that looks most realistic wins, which means that also the gradients get propagated back, and this expert gets trained to be even better at this kind of transformation. And if we do this, then we get a relatively fast learning process. So each color is an expert, and the graph shows the discriminator value that the expert achieves. So each plot is an expert, each color is a mechanism to be learned. So you see at the end, each expert has learned one mechanism, so higher is better, so higher means it's correctly, or it wins all these examples, and fools the discriminator. So that's good, and you can see also the dynamics. So the red one initially can't decide which task to learn, is it this one or this one, but then zooms in on this one, and then the green expert takes over here. And all this goes pretty fast. So overall, I think we had 32,000 of the MNIST examples. For each of them, we do 2 transformations, so 64,000 examples. And this is a single pass through this training set. And then afterwards, after training, we put some random inputs in that have been transformed. This is the output that the network then produces. And so this is the accuracy. If you take this kind of transformed digits and you put them into a standard MNIST classifier, the performance of the classifier will be around 40%. If you put the original digits in, the performance will be, as we know, close to 100%. And if we feed into this MNIST classifier the transformed digits, but processed by our network, then the performance converges to the optimum one relatively fast. So again, with like a single pass through this training set. And we can also handle cases where we don't know the number of experts. If we take too many into view, it also works. I think I should say this is an example. It's very simple, but the long-term goal is really to learn general structural causal models on multiple tasks in multiple environments. And I think these kind of models, they should reuse components that are robust across tasks. And I think a sensible inductive bias to find these kind of components is to look for causal mechanisms, because the world is made up of causal mechanisms. And I think also the competitive training could play a role in this. At least it looks quite promising. Okay, so I want to come to the conclusions. Overall, I like to think of causal models and statistical models as elements of a continuum of data modeling options. A statistical model is the weakest one, since it can only predict in IID settings, but the good thing is it can be learned from data. Now, at the other extreme, a differential equation model, that's maybe the gold standard in physics. It lets you do everything, but it requires a clever scientist and experimentation to come up with it. And I think for highly complex problems, it's often out of reach. Now, causal models are somewhere in between. I would argue they provide more insight, and they allow us to connect predictions to interventions, which provides a form of understanding that seems quite natural to humans, and we often communicate like that. So, and I think another reason for this is that humans and other animals use models not just for IID prediction, but we use models really to act in an imagined space, which is actually Konrad Lorenz's definition of what he calls thinking. Okay, so in conclusion, I have argued, or I believe that we build models, so I want to thank a number of people. I'll get these pictures, I'll stay up while I make my conclusions. We build models for the purpose of intervention. We often communicate them. If we want to communicate them, we often do so in causal language. Causal conditionals are the building blocks of causal models. They correspond to physical mechanisms. They are robust, they generalize across tasks, and the independent mechanisms assumption is one particularly, and I think, intriguing assumption that can be used both in inference and machine learning, and it leads to models that are made up of components and that are easier to understand what to do to the data, provided the underlying physical model is understandable in the first place. Okay, so with this, I want to conclude maybe with two plugs. One is, you might have seen, we have just published a book on causality. You can look at it outside at the MIT Press booth. And also we are always looking for people, so looking for postdocs for my Max Planck lab, and we just started an Amazon office interviewing, so we're looking also for scientists and engineers interested in causality and other topics. So thank you very much for your attention.
We have time for a few questions, so there's a mic over here, as well as a person holding a mic over there, Jason. So you can go up to either of the mics and ask questions to Bernhard.
Good talk, Bernhard. I have a question about speculating on symmetry. So if I can fix the variables domain, the logicians who think all variables are independent and seek to confirm dependence, and the statisticians who think everything's dependent and seek to confirm independence. So when I'm debugging, I tend to look to break causal chains that are artificial. When I'm confirming or explaining, I tend to want to confirm, just as you showed. Do you have any any intuition about how we can choose the design of those experiments to bias towards breaking causality that emerges or in confirming causality? Because those are two sides of the same coin. I hope they're symmetric.
Yeah, I think this question is too profound to be answered so fast. I think this is quite intriguing what you're saying, and very interesting. It's also connected to this difficulty of doing the testing. So if you want to test independence, as you know, it's extremely hard. It's even harder to test conditional independence. So somehow it's funny that we build these algorithms on the assumption that there exist conditional independence tests, even if in reality maybe we should be assumed that they don't exist, which would favor for the other direction. So I think this is very interesting. Probably it's connected to all sorts of things in philosophy of science and in inference of theories.
Or practically designing debugging tools.
And practically designing the debugging tools, I agree, yes. Interesting point.
Bernhard. So I want to return to the image that you showed of a cow on water, where you said that the fact that cow label was either at the very end or not present at all was perhaps indicative of having a non-causal model. Could you elaborate a bit further about why that's the case? Is this an image that is not drawn from the distribution it was trained on, for example? If you were to put it on that table that you showed and talk about really where the issue arises from, I'd love for you to dig in.
Yeah, so this is also a tricky thing. So I think, so one thing to say would be, there are, if you do your prediction based on confounding variables that are not, so that the beach is not directly a cause for the cow, or neither is it directly caused by the cow, it's just another variable that's somehow connected, and it's in this IID data set, it turns out that you can fool things. Maybe there are not enough of these examples in the IID data set. Therefore, even if training and test set come from the same distribution, it's such a hard problem that we don't have this kind of robustness. So I think in the end, we always, so I would argue all interesting problems are, if they are IID and we're in the limit, then they're not interesting anymore. It means we have to beat them to death with lots of data. So therefore, we should always assume that a system that should work well, and that should work in the sense of trying to achieve artificial intelligence, should have some robustness to generalize outside of the domain where it was trained on. Now, I would argue if a classifier is learning or mapping in the causal direction, so it's mapping from cause to effect, then it's easier to achieve this kind of robustness than a classifier that's using as input features either a confounded or other quantities that are correlated but not directly causally related, or effect features. And I think so this vision example is one like that. It's not the ideal example that I would like to have, because it's an anti-causal example in the first place. But I think it's an interesting point to discuss. So if you have a better example, tell me. But I think this one is also related to causality.
Is there an obvious sample complexity argument?
Well, you know, if you are in an IID setting, you can talk about sample complexity. And I agree, in that case, it's just a matter of having enough data. But I would argue it's not actually the most interesting setting, because we all know that we have universally consistent algorithm. If we have enough data, we can kill everything. But I think humans and animals usually don't have unlimited data, and from my point of view, it's more interesting to think about how we can learn from a small data set, and then it should be relevant to think about what is the underlying causal structure.
Thank you so much. Everyone thank Bernhard.